Okay. So let's start with a summary of last time. Last time we introduced what we called the Lagrangian. And it's given by T minus V. That's probably one of the most important definitions to remember from this class. All right, and this L here is called the Lagrangian. V is the sum of the potential energies. So it's the total potential energy of the system. Well, we looked at this last week. We only looked at one particle subject to a number of forces. And V was the sum of the potential energy from all those forces. And we'll see today that that's equivalent to having a system of many particles, and V is the total potential energy from all the forces on all the particles. And it won't be worth doing the math. And T is the kinetic energy. So again, it's either the kinetic energy for one particle, then it's just a half mv squared, or for a system, we'll see it's just the sum of all the energies of the particles in the system. You had a question, Jason? Okay. Oh, sorry, I did forget that I do have an announcement regarding assignment number 2. I've pushed the deadline back, so it was originally due this Friday, and I pushed it back by a week. So assignment 2 is due next Friday, which is the 17th. Let me write that here if somebody looks at the notes. I figured. Okay. Right, so the Lagrangian, this T minus V is given by the kinetic energy and the potential energy of the system. And then we saw that D'Alembert's equation, D'Alembert's principle, which we'd previously seen to already be equivalent to Newton's second law, with this new Lagrangian quantity, it turns out one can write the equations of motion as d by dt of di L by di qj dot minus di L by di qj. And that if there are forces in the system that are non-conservative, so that they can be written in terms of a potential, then this thing here is equal to the sum of the generalized forces that come from non-conservative forces. So it's I equals 1 to n sub c. So that's the sum of the number of non-conservative forces of Fi and C dotted with di Ri by di Qj. And so this is called either the Euler-Lagrange equation of motion, or sometimes just the Lagrange equation of motion. And there's one such equation per degree of freedom. And so that requires the Lagrangian to be a function of the generalized coordinates and the generalized velocities and potentially time. And then we did a few examples where we calculated for a mass going down an inclined plane, T minus V, and then we saw that we recovered Newton's second law for the equation of motion. And then we did another example, a more complicated example, where we wrote down the Lagrangian for electrodynamics. And it started by postulating the form of the generalized potential that would give rise to the Lorentz force. And then we saw that with that form of the generalized potential, when we applied the Lagrange equation of motion, we then obtained back the equation of motion that you would expect, namely ma equals the Lorentz force, so the electric force plus the magnetic force. So any questions about that material? All right. So now let's treat the case of multiple particles, and there's really not much to say because mathematically it's exactly the same math whether you have one particle and many forces or many particles each with a net force on them. And even then, each particle could have multiple forces on them. We saw this when we did D'Alembert's principle, that when you worked out the math, you had this kinetic energy term, and that kinetic energy could be summed over multiple particles. So if you remember D'Alembert's principle, which is what we've been using so far to get the equations of motion, we had d by dt of di t by di qj dot minus di t by di qj equals the generalized force qj, where qj was the sum over all the forces Fi dotted with di Ri, or the forces exerted by di Qj. And to get this equation with the Lagrangian, we had separated out the F into conservative forces that could be written as the gradient of a potential V, and non-conservative forces. And the forces that could be written in terms of a gradient of a potential with a V, we found that we could move them to the other side of the equation, and then instead of having a capital T, we had a T minus V, which we then called L. Okay? So if you have multiple particles, then you just have multiple kinetic energies, and we already saw the D'Alembert's principle. The T can be the sum of multiple kinetic energies. And similarly, there's no reason why the generalized forces can't be the sum of generalized, but come from the sum of generalized potentials. And so it's exactly the same math, except you now change what the index I means if you want to do this for multiple particles instead of multiple forces on one particle. So it's not worth doing it. And then you get, again, Lagrange's equation of motion, where T is the sum of the kinetic energies of all the particles, and V is the sum of the potential energies of all the particles. And we just generally call that the kinetic energy of the system and the potential energy of the system. So let's do an example with multiple particles in it. So this is example 4.3 from the notes. And it's just the two-particle example of the example we did last time. So we have an inclined plane with an angle theta. And we have two blocks on the plane. And they're connected by a rigid rod of length L. And it's a massless rigid rod. We have M1 here, M2 here, and we're simply told that we have forces of friction, F2 and F1. And so the question is, find the equations of motion. So the first question is, how many degrees of freedom? Oops. And so here, it should be clear that there's only 1 degree of freedom, right? You only need one variable to specify where the system is. And let's choose a coordinate system first. So let's place the origin at the corner of the wedge there. Say y goes up and x goes left. Oops. And if we want to draw a position vector for each of the masses, call that R1 for the first mass and R2 for the second mass. And so let's choose as our degree of freedom oops, I want to be in black. Let's choose a scalar, which we'll call R, and it's the magnitude of R1. So our first step is writing the transformation equations. So in principle, we have, if we're limited to the plane, we have two particles. So we have 2 coordinates for each particle, so in principle we have 4 degrees of freedom, right? So we have to specify x and y for both particles. So let's write out the transformation equations of those coordinates in terms of our generalized coordinate. So x1 is given by r cos theta. y1 is given by r sine theta. x2 is given by r plus l cos theta. And y2 is given by r plus l sine theta. Right? So to write the kinetic energy, we're going to need the velocities in terms of the generalized coordinate. So the only variable here is our generalized coordinate r. So theta and l are constants, right? So if I write x1 dot in terms of the generalized coordinate, I have r dot cos theta, since theta is a constant. Similarly, y1 dot is r dot sine theta. y2 dot is also r dot, or sorry, x2 dot first. x2 dot is also r dot cos theta, and y2 dot is r dot sine theta. And so the speed squared, because we're going to need a half mv squared for the kinetic energy, right? So we need v1 squared for the first particle. So that would be x1 dot squared plus y1 dot squared. And if I plug in r dot cos theta and r dot sine theta into here, I'll get r dot squared cos squared theta plus r dot squared sine squared theta. So cos squared plus sine squared is 1. And so then I get r dot squared. And similarly, v2 squared is also equal to r dot squared. So the total kinetic energy of the system, let's go on the next page, so T is a half m1 v1 squared plus a half m2 v2 squared, and that's equal to a half m1 plus m2 r dot squared, right? Now, the potential energy, V, is m1 g y1 plus m2 g y2. And that's m1 g. So now I plug in the equation which I had for y1, which is r sine theta. That's mg r sine theta. And then I plug in what I had for y2. So I have, that's m1, sorry, m2 g, r plus l sine theta. So let me now construct the Lagrangian. And the Lagrangian is then T minus V, a half M1 plus M2 R dot squared minus M1 G R sine theta the note has a mistake. The second term is also minus M2 times G R plus L sine theta. All right, and then the other thing that we're going to need, because there are non-conservative forces, before we can use Lagrange's equation and put the Q on the right-hand side, we need to figure out what the total conservative forces are, non-conservative forces. So we only have 1 degree of freedom, right? So the generalized force is the sum of I equals 1 to the number of non-conservative forces, which in this case is equal to 2, since we have F1 and F2. And it's given by Fi, non-conservative force, dotted with di Ri by di Qj. And then Ri vector is the location of where the force is exerted, right? So we have 2 forces, F1 and F2. So let's write the F1 force. So that's F1, its x component is F1 cos theta, x hat. And then it acts in the positive y direction, so it's plus F1 sine theta y hat. That's dotted with, so we only have 1 Qj, right? So Qj is equal to R. So that's dotted with di by di R of the first force is exerted at the first mass, so that's R cos theta x hat, that's the location of the first mass, plus R sine theta y hat, right? And then the second term, so the components of the F2 force will look the same, so F2 has a cos theta x hat component, F2 sine theta y hat, and that's dotted with di by di R of, now the force, the second force is applied on the second mass, and so the second mass has x position R plus L cos theta x hat plus R plus L sine theta y hat. So I now carry out the dot products and sum them. So the first dot product, I have F1 cos theta times R cos theta, right? Oh, it looks like it's wrong in the notes. Is it? Oh no, I have to do the derivatives with respect to R. That's fine. So if I do the derivative with respect to R, of the 2 terms that have derivatives with respect to R, you agree that it just removes the R, right? And on the second one, on F2, it also removes the L, because for example, if I look at the x component of the term that I've underlined, right, that actually has two parts to it. It's r cos theta plus L cos theta, both times x hat. And if I take the partial derivative with respect to r, the term that has just L cos theta x hat, that partial derivative is 0. Right, so when I take the partial derivative with 0, all it does is it makes both those terms be cos theta x hat plus sine theta y hat. And then I do the dot product, I get f1 cos squared theta, so that's f1 cos theta times cos theta x hat, so that's the x hat component, plus the y component, which is f1 sine squared theta, plus f2 cos squared theta, plus f2 sine squared theta. And of course, I can just use the cos squared theta plus sine squared theta equals 1. And the sum of the generalized forces is F1 plus F2. So the answer seems, it's like it seems obvious that it's just the sum of the forces, but it's not really that obvious, right? It's completely dependent on the choice of generalized coordinates. And it comes out simply as F1 plus F2 in dimensions of force, because we happen to have chosen a coordinate that's parallel to the forces. Okay, but it's not necessarily true that you should think that the generalized force is an intuitive thing that you can simply write down as F1 plus F2. But at least to me, it's not intuitive when that's true. Okay. So we have everything now, right? So we want to now put this into the Lagrange's equation of motion, or the Euler-Lagrange equations. So we want to write d by dt of diL by diqj dot minus diL by diqj equals F1 plus F2, right? Where again, qj equals r. So for the Lagrangian, we had, do I have it written on this page? Yes. So the Lagrangian here, the first thing we have to do is diL by dir dot. So there's only one term that has an r dot in it, and that's the first term. So diL by dir dot is m1 plus m2 r dot, right? And so I have, let's write out explicitly, I have d by dt of m1 plus m2 r dot. And then I'll have to do minus diL by diqj. So in the Lagrangian, both the terms that have r's in them have a minus sign in them, right? And they just have r as a constant, or a simple power of r, or r to the first power, I guess. And so when I do the minus diL by dir, since both terms are minuses, they're going to become pluses. The r is going to drop from both terms, and on the last term, the L is going to drop as well, right? Because you can look at the last term as two terms, m2g r sine theta plus m2g L sine theta. And m2g L sine theta doesn't depend on r, and so it'll just drop. Right, so I'm left with m1g r sine theta and m2g r sine theta. So I can actually factor the m1 plus m2 g sine theta. So if that wasn't okay to do it in my head like that, then let me know and I can write it out explicitly. So we're left with one time derivative to 2. So d by dt, m1 plus m2 are constant, so the only thing that depends on time is r dot. And so we have m1 plus m2 r double dot. I'm going to move the other thing to the other side. So I have it's equal to minus m1 plus m2. Oops, sorry, that's not equal to 0. That's equal to f1 plus f2. All right? So moving everything that's not accelerations to the right, I have f1 plus f2 minus m1 plus m2 g sine theta. And so that's exactly Newton's second law. So remember, R increases if the masses move upwards along the incline, right? So R has the same, the acceleration, or positive R acceleration has the same sign as the F1s and F2s. Of course, physically the system's going to move downwards if these are forces of friction. So I guess we didn't have to call them forces of friction. We could call them anything non-conservative forces. Oh, that's probably something I should change in the loads. Any questions about this problem? Which is a very slow way to do a very simple problem with Newton's second law. However, you can see that the method is very general, and you don't need to be thinking about forces and drawing vectors and anything like that, except maybe to handle the non-conservative forces where you have to do that dot product. But we'll stop considering non-conservative forces because most systems in physics are conservative. Okay. So next, we'll explore the connection to variational, I should call it variational calculus. In the notes they call it mechanics. Oops. Calculus. And the use of auxiliary conditions. Auxiliary only has one L in it. Okay, so at this point I hope you're convinced that it looks like we can describe systems in terms of this Lagrangian T minus V. And we saw that was equivalent to D'Alembert's principle, which we also saw was equivalent to Newton's second law, but the approach is conceptually very different, right? In vectorial mechanics, you think of forces, whereas in this analytic approach, you think of energies, kinetic energies and potential energies. And you just have these generalized non-conservative forces, which are a little bit annoying. We also introduced this concept of a generalized force, which is more general than a force in vectorial mechanics. We did some examples where we saw that the generalized force, for example, actually had units of torque or dimensions of torque. And so the definition of what a force is in analytic mechanics becomes a little bit blurry, and once you really stop thinking of them. So we've also noticed that the Lagrange equation of motion looks an awful lot like the Euler-Lagrange equation that you get from variational calculus. If you recall, let's say we have an integral that we call S from t1 to t2, so a definite integral of some function L integrated over dt, or we call S of the action. We found that if we wanted to find stationary points of that, and L depended on a set of independent coordinates, where t is the independent variable, and then L depends on, in mechanics, the generalized coordinates, which themselves depend on t. We found that for S to be stationary, then we get the Euler-Lagrange equations, which are d by dt of di L by di Qj dot minus di L by di Qj equal to 0. In this case, the Q's, remember, to get this equation, we explicitly require that the Q's could be varied independently. And so in the language of mechanics, we said that the system is holonomic. And so we've introduced constraints into the system. So we've eliminated all the variables that can depend on each other, and we're left with n independent generalized coordinates that can be varied independently. Now, when we did variational calculus, we found that we could somewhat relax that requirement that the QJs be independent with the use of auxiliary conditions. Remember, we had a set of coordinates and then a set of auxiliary conditions or constraints between the coordinates, and maybe in some cases it doesn't make sense to remove one coordinate in favor of the others. Maybe there's no sort of physical choice that makes sense why you would remove one coordinate instead of the others. And so we found this method of Lagrange multipliers that allows you to keep all the coordinates and treat them all as independent as well by adding in extra terms into the Lagrangian. And so we can do that here as well. We can sort of relax the assumption that the QJs are independent and incorporate into our problem the conditions that make those QJs dependent on each other with the use of these auxiliary conditions and Lagrange multipliers. So if we had a number of auxiliary conditions that are the form Fi of the generalized coordinates, we could write a new Lagrangian, or a new function L bar, which was given by L. So when we did variational calculus, we added the terms plus lambda 1 F1 plus lambda 2 F2 etc. But the lambdas are arbitrary, and so here in mechanics it makes a little bit more sense to put minus signs instead. So when you do this modification, so now, in principle, you could have eliminated k of the coordinates, but you decide to keep them and work with this modified function. Then you found again that d by dt of di L bar by di qj dot minus di L bar by di qj equals to 0 for all qj. If we compare this to the Lagrangian, this is the same as adding potential energies VI that would be equal to lambda I Fi, right? So what I've done is I've taken the Lagrangian L and I've removed and I've subtracted the minus lambda 1 F1. That's like subtracting, if I call lambda 1 F1 V1, right? So these lambda Fs, mathematically at least, look just like potentials. If they look just like potentials, then in principle, one could say that they have some force that's associated with them, with generalized forces. And those generalized forces would be given by lambda I d by dt of di Fi by di qj dot minus di Fi by di qj. And so here I've used the most general possible form of a force given by a potential, and that's the monogenic case. Remember, if it's just the conservative force, you would only have the second term, so the generalized force would be lambda I, would be minus lambda I di Fi by di qj. But in the one case where you have this generalized potential in electrodynamics, then we saw that you could add the second term. And so that's a little bit interesting, right? Because we can compare this to what we had before. So now going back from D'Alembert's principle and keeping the conservative forces as potentials V and non-conservative forces isolated, we had d by dt of di L by di qj dot minus di L by di qj was equal to qj. All right, so we see that this qj here somehow it has something to do with the constraints, these lambda Fs, right? And so if you think about it physically, this makes sense, right? Like a constraint in a physical system is generally associated with some sort of force. Rolling without slipping, it means that the surface of contact, there's some force that keeps them from sliding. A normal force is there's a force of contact. So let's say you have two, our classic example of two bars connected by a massless rigid rod, two balls connected by the massless rigid rod. The balls can't move with respect to each other because this is constraint of the massless rigid bar. So the mathematical constraint is that the distance between the positions of the two balls is fixed, but physically that means there is a tension in the rod that keeps the two balls at the same distance from each other. So this constraint on their position is associated with the force. And so that's generally true, although it can become a little bit obscure and hard to picture. So you can see here very generally that you have this relation, mathematically at least, where the constraints appear to be related to actual forces. For a complicated system, of course, you won't be able to figure out what the force really is, but for a simple system, we can. So let's do an example to highlight this. So this is example 4.4 from the notes. So let's assume we have an inclined plane. And an angle theta. We have a hoop of mass m and radius r, capital R. And that hoop rolls without slipping down the plane. Okay. So let's introduce a coordinate system. Let's use the same as before. Let's have y pointing up and x pointing to the left. And as we always do for these problems, we ask ourselves, how many degrees of freedom? Oops. So it's rolling without slipping. So if it's rolling without slipping, there's only 1 degree of freedom, right? You can tell where it is on the plane, and you can choose whatever you want. You could say the distance r from the contact point to the origin, and you could use that as a generalized coordinate. So let me draw the vector r, the position of the hoop, as the position of the point of contact. And one could use, there's only 1 degree of freedom, and you can use r. Now by choosing to use only the 1 degree of freedom r, we've implicitly in our heads taken into account a constraint. And the constraint is rolling without slipping. The hoop, in principle, as it turns, you can like paint a red dot on somewhere on the rim. And if you want to fully describe the hoop, you have to say where the hoop is along the plane and where the red dot is. So what is the angular displacement, phi, of the hoop? But in rolling without slipping, we know that r and phi are connected. But in principle, they could be independent. If it's slipping while it's rolling, then you do need both coordinates to describe the position of it. So let's, instead of using the 1 degree of freedom, let's actually use 2 degrees of freedom and a constraint. So let's choose to use 2 degrees of freedom r and phi plus a constraint. And we'll handle the constraints with this formalism of the Lagrange multiplier and see what kind of insight it gives us on the forces that are related to this constraint. So it turns out, if you recall, rolling without slipping is actually not a holonomic constraint because it's a constraint on the velocities. However, in a one-dimensional system, it can be integrated out. So the constraint, rolling without slipping, is the constraint that dr, so d little r, is big R d phi. All right, that means that the speed is instantaneously 0, right? dr minus r d phi by dt. And so we already did that in the introduction chapter. And so we saw that we can integrate this out to r, little r equals big R phi. And so I can write a constraint equation. So we have one constraint that depends on our 2 generalized coordinates, r and phi. And I need f to equal 0, so that means that f is equal to little r minus big R times phi. All right, so that's our constraint. So let's continue. So we want to write out the Lagrangian. So to write out the Lagrangian, we need the kinetic energy and potential energy in terms of our generalized coordinates, r and phi. So the kinetic energy, T, so there's actually 2 terms. It's a hoop that rotates, so it's a half I phi dot squared, right? The angular velocity of the hoop is phi dot, and it has a moment of inertia, I, plus a half the mass of the hoop times the speed of center mass squared. So I for a hoop is mr squared, right? And VCM, the speed of the center of mass, is simply r dot squared, where r is the distance it's the length of the vector r, right? So we can write out the kinetic energy as a half m big R squared phi dot squared plus a half m little r dot squared. The potential energy is the mass of the hoop times g times the y position of the center of mass. So the y position of the center of mass is going to be r sine theta. So r sine theta puts you at the contact point, right? And then there's going to be a constant offset, and we'll call that k. That's the offset from the center of the hoop to the contact point. And so that's just constant, right? It doesn't matter where the hoop is along the inclined plane. The center of the hoop is always going to be vertically offset by the same distance from the point of contact.
Yeah, isn't that just the radius of the hoop?
Question, Michelle? It's the radius of the hoop times like cos phi or something, right? because it has to go in the vertical direction.
Okay.
But I'm too lazy to figure out exactly what it is because it doesn't matter. So you remember the potential energy, gravitational potential energy, the only thing that can ever have a physical impact is the change in potential energy. So it never matters where you put the origin for potential energy. And here, we know we're going to apply the Euler-Lagrange equation. And the Euler-Lagrange equation is going to have di-L by di-R dots, di-L by di-Rs, di-L by di-Phis, and di-Ls by di-Phi dots. So any term that doesn't depend on R or Phi, or R dot and Phi dot, ultimately when we do the equations of motion is going to drop out. So when we do di-L by di-R of mgr sine theta plus k, since k is a constant, the k is actually going to drop out. And we'll see later when we look at the properties of the Lagrangian that one can always add a constant term to Lagrangian without changing the equations of motion. And so I'm just going to put the k in, but I know it's going to disappear right away when I take the derivative, so I'm not even going to bother figuring out what k should be equal to. I hope you find that acceptable. So this gives us the Lagrangian L to be t minus v, right? So it's a half m big R squared phi dot squared plus a half m little r dot squared. That's t minus v mg. I guess I'll keep the k in for now, but I know it'll disappear very quickly. So now our prescription, right, is we have two generalized coordinates, r and phi, and as is, we cannot vary them independently unless we add in a Lagrange multiplier. So let's build our modified Lagrangian, which I'll call L bar, and so that's simply the initial Lagrangian, mr squared phi dot squared plus a half mr little dot squared, or little r dot squared, minus mg r sine theta plus k, and then minus lambda, and our function f was just given by r, little r, minus big R times phi. So we only have one constraint, so I have a lambda 1 f1, and we wrote out f up there, the constraint for rolling without slipping, and we put it into our modified Lagrangian. So the next step now is to apply the Lagrange equations. So we need d by dt of di-L bar by di-Qj dot minus di-L bar by di-Qj equal to 0. And we're going to have two such equations because we have Qj equals R or phi. So let's do the case for R. So I look at the modified Lagrangian, and there's only one term that depends on little r dot, right? And that's the half m little r dot squared. So if I do di-L by di-R dot, I get mr dot. And then if I take d by dt of that, I'm going to get mr double dot since m is constant. So that first term becomes mr double dot. All right. Now I have to look for the terms that depend on r. So I have on little r. So I have on the Lagrangian, I have a minus mg r sine theta. Well, let me just write it out. L bar. Let's write it here. R squared phi dot squared plus a half r dot squared minus mg sine theta r plus k minus lambda times little r minus r phi. Alright, so the terms that depend on r, and I have to do a minus then, so I'm going to have a plus mg sine theta, and the r is the first power, so it drops, and then plus di by di r of lambda r, which just gives me lambda. And so that's got to equal to 0. And let me do the same thing for phi. So if I do it for phi, in terms of phi dot, I only have the first term, and so that's going to give me an mr squared phi double dot. Is that right? That's the wrong r, that's why. It's m big R squared phi double dot. And then the only other term that depends on phi is the minus lambda times minus r phi. So that's plus lambda r phi in the modified Lagrangian. Derivative with respect to phi is lambda r. And then I switch to sign because there's a minus di-L by di-qj. And so that gives me minus lambda r, big R, equal to 0. So I have two equations and three unknowns. Spelled known wrong. So what are the three unknowns? Obviously lambda, but then the r dot and r double dot and phi double dot, right? We want to know the accelerations so that we can write a system of ordinary differential equations that we can solve. All right, so the three unknowns are r double dot, phi double dot, and lambda. So if we go back to variational calculus, we'll remember we do have one more equation, and that's our equation of constraint. So our equation of constraint is that r, little r, equals big R times phi. With the equation above it, this doesn't really help me eliminate one of the variables, right? Because this does not connect r dots and phi dots. But you can take the derivative with respect to time twice of that equation. And that's pretty generally true that you have to take the time derivative of the constraint equation to get the third equation, or the nth equation to get the unknowns. So that just tells me that r double dot is r phi double dot. And now we can get rid of the unknowns, right? Now we have three equations, three unknowns. So let me take the phi equation. So if I take the phi equation, I have mr squared phi double dot minus lambda r equals 0. That's the same as m big R, little r double dot. All right, so I've just substituted in phi double dot equals 1 over big R, r double dot. equal to lambda r. So if I put that into the r equation, I have m r double dot plus, mg sine theta plus lambda equals to 0. Now let's say I want to solve now for lambda to get some insight of what this lambda means. So from here I have lambda equals mr double dot, right? And so I have lambda plus mg sine theta plus lambda equals 0, or lambda equals minus a half mg sine theta. And so what is this lambda equal to minus a half mg sine theta? Well, remember somehow lambda is related to this constraint of rolling without slipping. Something to do with the force that's related to rolling without slipping. And so lambda is equal to 0 if theta is equal to 0. So if theta is equal to 0, the hoop's not going to rotate because it's on a flat surface, so it doesn't want to turn. This lambda is something related to a force that wants to make the hoop turn depending on the angle of the incline of the plane. And so we can sort of attribute a physicalness to what this is, what this lambda is. So now I can rewrite our equations of motion, now that I know what lambda is equal to, and remove lambda from the equations of motion, which is ultimately what one would want to do to describe the system, right? So if I write the r equation again, then I remove the lambda from the system instead of removing the r, I get mr double dot equals mg sine theta, or plus mg sine theta plus lambda, and lambda is minus a half mg sine theta, so that's mr double dot plus a half mg sine theta, and if I can move that to the other side, I now get mr double dot equals minus a half mg sine theta. And I can do the same for phi. And in the phi equation, you get mr squared phi double dot. That's just going to be equal to lambda r, right? And so that's minus a half r times mg sine theta. So recall, the moment of inertia is I is mr squared, right? So the second equation is something like I and phi double dot. Maybe in undergrad mechanics you might have called that alpha for the angular acceleration. So the second equation of motion that we got is of the form I alpha equals minus a half r mg sine theta. And that kind of looks like tau. All right, that's the equation that you get from, that you would have done in undergrad physics for a rotational system. You'd have written I alpha equals the sum of the torques. And so here we can see that this torque, in this case, is R times lambda. So we see that lambda is connected to this force that makes the hoop rotate. In fact, lambda R is the torque that makes the thing rotate. So we didn't need to do two different coordinates for this system, right? We could have just done R or phi because the two are directly connected to each other. But instead, we chose to use both of them with this method of Lagrange multipliers. And then we saw that this Lagrange multiplier is associated to the force that gives rise to the constraint, in this case, rolling without slipping. And we had this insight because we noticed that the D'Alembert's principle, or the Lagrange equation with the non-conservative forces on the right-hand side, looks exactly mathematically like the problem of finding the stationary value of an integral subject to a constraint. And so this is the formalism that you need to do in assignment 2 for one of the questions. All right. So let's finish this by calculating the generalized forces, Qj, which are given by lambda. So there's only one constraint. That's d by dt of di f by di qj dot minus di f by di qj. All right, remember we got that earlier, this equation here, where f is equal to little r minus r phi, and qj is equal to either r or phi. So this means that we have a qr, which is lambda times, so f doesn't depend on any of the velocities, right? So it's just minus di f by di qj. And so for r, it's the derivative with respect to r is just 1, right? And so qr is simply equal to minus lambda. And so qr is mg sine theta. So that's the generalized force in the r direction. And q5, if we wanted to calculate it, would be equal to lambda times r, right? The d by d phi of f is just r, and I have to do minus of that. And so we get minus a half mg sine theta r. So q phi is equal to the torque. So this generalized force, which you can express in terms of the Lagrange multiplier times this term, remember we identified that the lambda k, fk's that we're adding to our modified Lagrangian could be thought of as additional potential energy terms. And if there are additional potential energy terms, then we can write a force that's associated with them. And we'll call that force the generalized force in that direction. And then you get these two generalized forces in the r and phi direction. So the one in the r direction is a little bit not super obvious what it physically represents, but the one in the phi direction is pretty clearly the torque. Okay? So I think I'll leave it there because the next problem is, again, the same thing but much longer. But what we'll do in the next problem, what we just did here, where was it? We examined a hoop rolling down an inclined plane, and we used 2 degrees in freedom instead of 1. And then we added the constraint of rolling without slipping which in principle would remove one of the degrees of freedom. But actually there's 3 degrees of freedom, right? You could describe the hoop by the x and y position of the center of the hoop, and phi, the rotation of the hoop. And so this, there's 3 degrees of freedom, and the reason we reduced it earlier, where I didn't really emphasize it, is that we also constrained the hoop to roll along the plane. So there's another constraint here that the contact point of the hoop is along the side of the inclined plane. But that can also be included as a constraint. So what we'll start with next week, or Wednesday, is we'll do the same problem again, but now we'll use 3 degrees of freedom, the x and y components of, or positions of the center of mass and phi. And we'll see how the constraint of going along the plane also gives additional forces. Okay, any questions about that? Let me reiterate that the assignment 2, the date is changed. Instead of being due this Friday, it'll be due next Friday. So we have this week of class, next week of class. So at the end of next week of class, assignment 2 is due. And then the week after that, on the Monday, we'll do a revision. And on the Wednesday, we'll do an in-class midterm. So I warn you that the midterm will be in class. I think it's October 21st or 2nd, something like that, whatever the Wednesday is. Okay? Any questions? Okay, well, thanks everyone for joining, and I'll talk to you all on Wednesday.